With Neptune raising worries among researchers and space fans, the same famous specialists, including Neil deGrasse Tyson and Michio Kaku, have sounded cautions about the possible outcomes of this heavenly conflict. Yet how did Pluto arrive at a course of action with its far-off neighbor? And what could this infinite crash mean for us here on the planet? How about we investigate this unfurling occasion? Once thought to be an undeniable planet, Pluto was subsequently renamed a dwarf planet because of its unique orbit. In spite of this reclassification, it continues to enthrall and attract stargazers. Ongoing forecasts from prominent scientists highlight the proximity of Pluto's path to that of Neptune. These specialists warn against a possible collision between the two planets, representing a potential danger to Earth. Pluto's journey around the Sun is marked by its unmatched attributes within our planetary group. Its orbit spans a broad 248 years, and since its discovery in 1930, Pluto has yet to complete a full revolution. Adding to its intrigue is the highly elliptical shape of its orbit, a sharp contrast to the nearly circular orbits of the major planets. Additionally, Pluto's orbit is tilted 17 degrees to the ecliptic plane, making its path more extreme compared to other planets. One remarkable feature of Pluto's orbit is its crossing of Neptune's path. For roughly 20 years in each cycle, Pluto ventures closer to the Sun than Neptune, defying expectations given their respective positions in the solar system. So why hasn't a collision occurred between Pluto and Neptune? The explanation lies in the gravitational effects exerted by other planets. The study of Pluto's orbit began soon after its discovery, revealing a puzzling trajectory for astronomers. Unlike most planets whose orbits lie relatively close to the ecliptic plane, Pluto's orbit has a steep inclination and elliptical shape. The mystery deepened when astronomers realized that Pluto's orbit intersects with Neptune's. The stability of Pluto's orbit, despite these complexities, serves as evidence of the intricacies inherent in space mechanics. The three-body problem in celestial mechanics, dealing with the motion and gravitational interactions among three bodies like Pluto, Neptune, and the Sun, helps explain the complex dance of their paths and forces. Terms like resonance, libration, asynchronous libration, and the VZK wobble contribute to understanding this cosmic puzzle. Astrophysicists affirm that asynchronous libration plays a critical role in maintaining the safe orbital paths of Pluto and Neptune. This means that when Pluto reaches the point where it crosses Neptune's orbit, it is positioned at least 90 degrees away from Neptune, crucial for preventing collisions. Libration ensures that when Pluto approaches Neptune or other giant planets, it is aligned above or below their orbital plane, adding another layer of protection. The VZK wobble explains why Pluto's orbit around the Sun appears erratic but eventually stabilizes. Despite this apparent irregularity, mathematical simulations from the late 1980s revealed that Pluto's orbit, though chaotic, remains stable over extremely long timescales. Small initial variations can lead to major differences over millions of years, yet Pluto's orbit holds steady due to the gravitational influence of massive planets like Neptune, Jupiter, and Saturn. Neptune's special relationship with Pluto, completing 3 orbits for every 2 of Pluto's, adds stability to Pluto's trajectory. Jupiter's massive gravity also plays a significant role, while Saturn's smaller but notable influence contributes to the overall effect. Rigorous simulations have shown that the combined gravitational forces of these 3 giants ensure Pluto's safe, stable movement through space for billions of years. These phenomena are essential for maintaining the order and consistency of celestial mechanics. Without them, the solar system would be more susceptible to chaos and unpredictability, potentially resulting in collisions or planetary ejections, with ripple effects throughout the cosmos. Understanding Pluto's orbit is especially important in light of discussions about a potential future impact with Neptune. This knowledge provides a clearer view of the unique and dynamic nature of our planetary system. Pluto's case highlights how seemingly unstable orbits can achieve harmony through complex gravitational interactions. Continued observation and study of these phenomena are essential for understanding our place in the universe. Exploring the depths of space often reveals the eccentric nature of celestial bodies, and Pluto's orbit is a prime example of this unpredictability. The concept of orbital chaos vividly illustrates the delicate dependence of a celestial body's trajectory on its initial conditions. In Pluto's case, even minor variations in position or speed can significantly alter its long-term path. Computational simulations have been instrumental in helping scientists understand Pluto's motion. By making small adjustments to these initial conditions, astronomers have gained insight into how subtle changes can profoundly influence Pluto's trajectory. In the late 1980s, these simulations revealed fascinating aspects of Pluto's orbit. Despite stabilizing factors like resonance, libration, and asynchronous motion, Pluto's path can still behave erratically. Even a tiny deviation in its initial position or speed can lead to dramatic long-term changes. Nonetheless, Pluto's orbit remains remarkably stable over billions of years, an extraordinary feature that underscores the hidden order within apparent chaos. This suggests that, beneath its seemingly erratic motion, Pluto's journey around the Sun follows a structured pattern. When predicting cosmic events, especially involving planets with unusual orbits like Pluto, this inherent unpredictability makes long-term forecasts difficult. Mathematical simulations help us understand and anticipate the future paths of celestial bodies. But they also highlight our limitations, as these models rely heavily on precise initial data and replicate complex interactions. Even a small error can lead to vastly different outcomes. Forecast. Troublesome, the tumultuous nature of heavenly circles, such as Pluto's, helps us to remember the ever-changing universe. While we've made progress in understanding space, Pluto's case features our continuously limited information. The tremendousness of interstellar distances and the shortage of planets in open space act as impediments against incessant impacts. Furthermore, rebel planets are relatively unprecedented compared to the quantity of planets and stars in stable circles, making such experiences much more unrealistic. Comprehension of the gravitational impacts of giant planets on Pluto's circle provides important insights into the broader dynamics of the nearby planet group. It exhibits how every planet's presence and position can influence the direction and stability of different bodies in the system. In spite of these complicated powers, significant astrophysicists are expressing worries about a possible collision between Pluto and Neptune. This raises inquiries about why such an impact, which appears to be far-fetched given these complex elements, is presently a subject of concern. Neil deGrasse Tyson, a notable astrophysicist, offers an extraordinary perspective on the secrets of our solar system, particularly with regard to Pluto. Tyson, popular for renaming Pluto as a bantam planet rather than an undeniable planet, shares wise considerations on how our understanding of heavenly mechanics is continuously developing. Tyson sees Pluto's renaming not as a downgrade, but rather as a fundamental acclamation to our expanding knowledge of the various objects circumnavigating the Sun. His approach to divine mechanics includes consistent learning and transformation. He sees the intricacies of circles like Pluto's as an indication of how much more there is to discover in space. Tyson trusts that the charm of these questions is what makes stargazing so dazzling. Moreover, Tyson knows how space-related occasions and discoveries influence public fascination with space science. He thinks events like Pluto's renaming and its surprising orbit are chances to capture the public's creative mind and interest in the universe. By talking about the dynamic and at times strange perspectives of space mechanics, Tyson aims to cultivate a deeper appreciation and comprehension of the universe. Neil deGrasse Tyson opens a window for the general public to wonder at the marvels and mysteries of the universe. Working alongside other researchers, Tyson actively alerts the public about the possible risk of Pluto's capricious path. After broad investigation of Pluto, he has raised concerns that the three-body issue could represent a genuine danger, proposing that an impact with Neptune would be extremely overdue. Furthermore, Tyson underscores how such a crash could disturb the equilibrium of the universe and lead to horrendous outcomes reaching Earth. An impact between Pluto and Neptune would be a strange and catastrophic event in our nearby planet group. This impact would release a monstrous amount of energy, potentially shattering Pluto due to its smaller size and icy composition. Debris from the impact could disperse across the planetary system, presenting potential dangers for different planets and their moons. For Neptune, such an effect could potentially change its climate and orbit, depending on the specific details of the crash. Michio Kaku, a notable theoretical physicist recognized for his work in string theory and science communication, offers an interesting viewpoint on this situation. His perspectives on the future of space exploration and the association between heavenly mechanics and theoretical physics provide profound insights into phenomena like Pluto's orbit. Kaku sees the study of Pluto and its circle as a glimpse into the future of space exploration. Understanding the complex gravitational interactions and orbital dynamics of celestial bodies like Pluto, according to Kaku, can offer critical insights for future space missions. This information can help with navigating the planetary system more effectively, anticipating potential risks, and planning missions to the outer edges of our planetary system and beyond. Kaku emphasizes that the lessons learned from studying Pluto's orbit can be applied to the exploration of other celestial bodies, providing a framework for understanding and approaching faraway universes. In examining the physics of planets, Kaku frequently highlights the deep connection between heavenly mechanics and theoretical physics. He believes that the movements and interactions of planets, like the gravitational dance between Pluto and Neptune, are not isolated events, but are connected to fundamental principles of physics. Kaku's work in theoretical physics, particularly in string theory, aims to understand these principles at the most essential level. He proposes that contemplating the intricate details of divine mechanics, like Pluto's orbit, can yield insights into the basic laws of the universe. Like Tyson, Kaku has also focused on the potential impact such a collision could have on his theories about the universe. If Pluto and Neptune were to collide, it would be a critical event in astronomy, offering a remarkable observational opportunity that could potentially contribute to our understanding of string theory. String theory, a theoretical replacement of the framework of point-like particles with one-dimensional strings, seeks to describe the fundamental forces and matter in the universe. A crash of such magnitude in the nearby planetary system could create extreme states of energy and gravity, offering insights into the behavior of fundamental particles and forces under extraordinary conditions, a key focus in string theory. Moreover, the gravitational waves released by the impact could provide significant data for testing predictions of string theory related to gravity and spacetime. While the direct effect on Earth would be minimal due to our distance from the outer planetary system, the scientific implications of such an event could be substantial, potentially contributing to our understanding of the fundamental nature of the universe, as described by string theory and other areas of theoretical physics. Pluto's orbit serves as a striking example of heavenly mechanics, displaying both stability and chaos within our nearby planetary system. The exceptional qualities of its gravitational pull and orbit, particularly the influence of neighboring planets like Neptune, highlight the complex and dynamic nature of space. The universe holds a great number of secrets, and the three-body problem is only one of them. There are other potential disasters that researchers anticipate. While the chances of planets crashing in space are very low, it's not completely impossible. The way planetary orbits are affected by various factors, including gravitational interactions, is explained by the three-body problem. In some space systems like TRAPPIST-1, with 7 Earth-sized planets, gravitational forces create a rhythm pattern brought about by orbital resonances. Over time, these patterns can make planetary paths less stable, potentially leading to collisions. Despite the crowded nature of systems like TRAPPIST-1, impacts are not currently occurring. Researchers closely monitor these systems to understand how planets influence each other's paths, especially when they are close. This information helps us appreciate the development of planets in space. Rebel planets, drifting through space without orbiting a star, introduce an additional unpredictable element. These planets, once part of a star system, are ejected due to gravitational disturbances or other cosmic events, such as the nearby passage of another star or dynamic shifts in various systems. Over the long haul, these wandering planets can traverse vast distances, possibly reaching regions far from their origin. During their solitary journey, there is a possibility of encountering other star systems. If one of these rogue planets enters another nearby planetary system, there is a slight chance of a collision with a planet in that system. However, given the vast and predominantly empty nature of space, the likelihood of a rogue planet directly impacting another planet is extremely low.